All right, let's dive right into this explainer, unpacking a massive new survey that bridges the gap between two of the most powerful tools in artificial intelligence. Now, if you've been following AI news, you know we've gotten really good at processing data. But organizing it logically and, more importantly, safely in high-stakes environments, yeah, that is still a massive challenge. So today we're looking at a groundbreaking paper published in Scientific Reports that proposes a comprehensive new framework for how we combine structured knowledge with neural network processing.
It really all comes down to this. What actually happens when the rigid, structured logic of knowledge graphs collides with the raw pattern-finding power of neural networks? It's like merging two totally different universes. We're going from the messy, unstructured reality of raw AI data to a perfectly mapped taxonomy. For the longest time, one was great at defining rules, and the other was great at finding hidden patterns. But as you'll see, when you merge them, you unlock capabilities that are literally critical for everything from enterprise search to preventing catastrophic industrial meltdowns.
Here's our roadmap for today. We'll start with graphs meeting neural networks, then look at the four-stage AI pipeline, jump into an industrial faults high-stakes test, peek inside the KGEI-GNN model, and wrap up with the future of graph AI.
Part 1. Graphs meeting neural networks, building a unified framework for AI.
To make sure we're all on the exact same page here, think of knowledge graphs as basically the ultimate map. It expertly outlines how every single piece of equipment, every symptom, and every component connects within a complex system. It is purely logical, it's symbolic and structured. It's basically a domain expert's brain translated directly into a graph of nodes and edges, where relationships like causes or co-occurs with are explicitly defined.
Now, if the knowledge graph is that map, then the graph neural network, that's your high-powered GPS engine. GNNs calculate the most critical patterns across that terrain. They don't just look at a single piece of data in a vacuum. They aggregate features from a node's entire neighborhood, which allows the AI to deeply understand contextual behavior. But the thing is, historically, deploying this engine onto that map has been highly fragmented.
The wild thing is, until this comprehensive survey hit Scientific Reports, we literally lacked a unified way to understand how these two technologies interact across the board. The researchers noted that developers were essentially flying blind, treating GNNs as just this monolithic block, rather than picking the right specific architecture for the right stage of data processing.
Moving on to Part 2, the four-stage AI pipeline, mapping the taxonomy.
The survey breaks down the entire AI lifecycle into these four distinct stages: construction, embedding, reasoning, and applications. This flow guides data all the way from noisy, incomplete extraction straight through to real-world industrial diagnostics. By mapping the pipeline out like this, the researchers force a direct comparison between what a specific stage demands and what a specific neural network model can actually deliver.
If you're a developer, here is your rapid-fire cheat sheet. Doing construction like extracting entities from messy data? Grab a graph convolutional network, a GCN, for that sweet baseline stability. Moving to the embedding stage? Swap over to a graph attention network, or GAT, because it dynamically weights relational importance and filters out the noise from low-signal edges. And for reasoning, where you have to infer missing links, hierarchical GNNs are your absolute best bet, since they preserve structure over those long multi-hop dependencies.
Now, if you're the one actually building these pipelines, the survey insists on some hard, actionable rules. First, knowledge graphs evolve, right? So if you aren't monitoring embedding drift in production and retraining on rolling windows, your embeddings are going to totally misalign with your updated schemas. And honestly, this is huge. Pin your GNN library versions. Graph architectures are evolving so fast right now that dependency drift can completely break your neighborhood aggregation logic.
All right, Part 3, industrial faults, a high-stakes test in preventing catastrophic failures.
We are talking about the big leagues here, keeping massive, complex systems running smoothly. And in these environments, traditional deep learning just flat out fails. Why? Because it relies way too heavily on perfectly labeled data, it lacks explainability, and it's super sensitive to background noise. I mean, when a machine is shaking violently, standard AI really struggles to tell the difference between normal operational vibration and a critical bearing failure.
So, to pressure test the ultimate proof of concept for mixing knowledge graphs and GNNs, the researchers used two incredibly dramatic, volatile datasets. First, a three-phase flow facility simulating pressurized water, oil, and air through pipes monitored by 24 sensors. Second, a literal nuclear power system dataset containing encrypted time series telemetry covering turbines, valves, and steam generators across 121 different sensors.
4 Hertz.
That is the incredibly fast recording rate of the sensors tracking the nuclear power system. That means 4 complete snapshots of 121 complex sensors every single second, constantly hunting for an anomaly before a total meltdown occurs. The sheer amount of noise and overlapping data happening here is just staggering.
Which brings us to Part 4, inside the KGEINN model, moving from correlation to causation.
Enter the KGEIGNN. Yeah, absolute mouthful of an acronym. But it stands for Knowledge Graph-Based Exogenous Intervention Graph Neural Network. What it actually does is fuse human expert knowledge directly with live sensor data. This transforms raw signals into a spatiotemporal graph that genuinely understands cause and effect, rather than just blindly spotting random patterns.
Here is the massive difference between standard models and this new approach. Standard GNNs, they aggregate neighborhood features completely blindly. If a sensor is sitting near a noisy machine, the AI just absorbs that noise, creating false correlations, what data scientists call confounding variables. The KGEIGNN, on the other hand, applies exogenous intervention. It uses statistical techniques to isolate the true fault signatures from normal operational variants. It's basically like putting noise-canceling headphones on the AI.
And the performance leap is just wild. In that pressurized pipe dataset, the 3-phase flow facility, KGEINN completely dominates. It hits a 96.14% accuracy, vastly outperforming baseline models like IIGNN and PKTM-CNN. And it's not just finding faults generally. It is accurately classifying exactly which of the 6 fault types is happening, with near perfection.
That advantage totally holds up even in our second, much tougher environment. In the chaotic, highly complex nuclear power system dataset, the causal intervention of KGEIGNN maintains a clear lead, hitting 89.39% accuracy across 22 different fault conditions. The researchers even ran an ablation study, which is where they turn off parts of the AI to see what breaks, and they found that if you remove that causal intervention module, the accuracy just plummets. The causal reasoning is exactly what makes the whole thing work.
Finally, Part 5, the future of graph AI. What comes next?
So where do we go from here? The paper maps out the exact next steps for researchers and engineers. We desperately need to focus on sparsity-tolerant aggregation, meaning we need models that won't fall apart when sensor data goes missing or the edge density of the graph drops. They also flag a huge operational need, containerizing GNN inference services. These graph models process massive adjacency matrices that scale non-linearly. So if you don't bound memory access, you risk system crashes during peak data ingestion. And obviously, in an industrial plant, that is unacceptable.
I want to leave you guys with this one thought. Is your AI just finding patterns, or is it actually understanding causes? Because as we've seen today, true safety and innovation require models that do a whole lot more than just guess. When we finally merge the logical map of knowledge graphs with the processing engine of graph neural networks, we start moving away from AI that just correlates data toward AI that truly understands why things happen. Thanks for joining me on this explainer, and I hope it changes how you look at the future of structured AI.